G'day, Peter Solby here, back again with another video on Peltier devices. Now I have been making a few videos on the theoretical side of things, and this was never really my intention. I did want to do what I called a video blog on my weekend hobby, which was just playing around with Peltier devices. I seem to be getting better results than most of the experts were predicting, so I thought I'd just share the circuits that I was making as well as the measurement systems and stuff like that. Just have a bit of fun, really. I got sidetracked into the theoretical world, and I thought for this video anyway, I'd go back to the original roots and just do an experiment. So the experiment this time is going to be cooling a can of beer, one of my favorite pastimes, and I have done it a few different ways before, so I just had a new idea here and I thought I'd make a video about it. And when I talk to my friends about this and I say, I want to use say 20 or 30 watts of electricity to cool this down in 20 or 30 minutes, they're like, anything special there, Peter? What are you talking about? 20 or 30 watts? What does that mean? And I completely understand that. You know, for people that are not thinking about this kind of thing 24/7 like I do, yeah, it doesn't sound all that impressive. So I'm going to break this video up into 4 parts. The first part is going to explain why I think that is a fairly decent feat to cool it down in, say, 20 minutes or 25 minutes. Secondly, I'll talk about the actual idea and the experiment itself. Thirdly, I'll give you the results. And fourthly, just talk about some of the ideas I have to improve the setup. So basically, that's it. I think it's going to be a fairly short video, but anyway, let's get into it. So here's the deal. I like beer, but as an act of self-preservation, I tend to keep the house empty of beer from Monday to Thursday, and then around 5 o'clock on a Friday afternoon, I'll jump on the bike and go down to my local grocery store and pick up some beer there. Or if I'm feeling a little bit energetic, I might go all the way to Don Quixote, where they have the good quality beer, but they have cheaper prices. The trade-off is that it's at room temperature. So my options when I get back home could be to put it in the fridge, where it might take as much as 4 hours to chill down to drinkable temperature. Or I could stick it in the freezer, where it takes about 45 minutes, but I have to be really careful there because I can easily freeze the beer. So this is your classic beer drinker's dilemma on a Friday afternoon. So what's the deal there? Why does it take so long to cool a can of beer in a fridge? Well, it turns out to be not due to the thermal mass of the can itself, or the whole the can and the liquid, of course. It's about 1,500 joules per Kelvin, which means you need 1,500 joules to change the temperature by 1 degree. So if I want to get this down by 20 degrees, roughly speaking, that's about 30,000 joules or 30 kilojoules, which sounds like a lot, especially if you're talking about a cooling system here that has about 30 watts of cooling. But that 30 watts is 30 joules per second, and if you run the numbers, it's about 1,000 seconds. 16, 17 minutes, that's, you know, plenty. I'm happy to wait 20 minutes to get my can of beer on a Friday afternoon. So as long as I can get that 30 watts out of here, it should be fine, even if I start off at room temperature. What's the problem though? It has to do with thermal resistance, and I've mentioned this before with my Peltier setups, that's really the bugbear that's restricting a lot of systems, and it's the same thing here that's causing the problem. So water, so this is mostly water in here, it has a thermal conductivity that is about 500 times less than normal metals. In fact, if you compare copper to water, it's a factor of 650. So water is just a hopeless conductor of heat. It's really surprising because the thermal capacity, the heat capacity, is it's on par or even better than metals, but its thermal conductivity is just terrible. And then of course on top of that you have air around here, which is orders of magnitude again less conductive. Put all that together and it's not a pretty picture. This is going to take a long time to cool this down. Now, people that want to get around this problem, they might use an ice bath, but even there, if you want to cool it down quickly, you'll need to move this around every now and then, because otherwise it'll just cool the outside layer of the water that's in here, but it won't cool the inside part there. So mixing it around. If you want to get even better, you can put salt into the ice bath, and that can reduce the temperature down to -5 or -10 degrees. So that will speed it up again a bit more. But again, you still have to move it around every now and then. Otherwise, you're going to get this sort of layering effect of warm water in the middle and cold stuff on the outside. Both of those options anyway are using massive amounts of electricity to create the ice in the first place, and then you've got salty ice water and stuff like that. For me, that's not a great option. So that's the segue into the next section here. So I'll explain my idea how I'm going to get over this problem of trying to get good thermal contact with the can and the liquid inside of here. So hopefully that made sense. So we'll kick on to the next section. So some of you will know I did a video recently on, not recently, I think it was 2 months ago now, but it was dealing with the Peltier fridges, the blue and the white fridge and the parabolic curve there. That was part of a bigger video that I was trying to work on, where I had in the middle of the video an experiment where I was trying to cool the cans a bit down a bit quicker. And in that experiment I had 6 cans sitting in a tray of water. That tray of water was being cooled by a Peltier system. Unfortunately, it didn't work that well. Again, because the thermal resistance was preventing the cold water at the bottom here from moving up to the top of the can here. And especially, you're not going to get any convection or circulation in there because the cold stuff is already at the bottom. So I thought I'd move that around, and I'd have the water actually come on top of the can here. So that's basically the experiment here. But in addition to that, I thought I'd tilt the can on one side. The reason for that is I think there might be just a little layer of air or CO2 that could be at the top of the can there that might prevent the cooling from going from the top here down into the liquid itself. So tilting it on its side should guarantee that there's some liquid here on the other side of the aluminium there that should transfer that the cooling through. And then on top of that, I just thought this angle here might help to break up the stratification that can occur. So even if you do apply cooling to the top of the can here, it kind of set up levels inside here, stratification that can prevent the normal motion of the cooler liquid at the top here will fall to the bottom, but it doesn't do it so efficiently in that kind of layered stratification there. So by having it on a tilt here, just my intuition is saying that that should break up that stratification a bit more. So you get the colder liquid here, should want to fall down the side of the can here and help to push the warmer water up here. It will also want to travel up because of the lower density, so I want to move up, and hopefully that should set up kind of circulation inside there. Does it work? I don't really know, because you can't really measure inside the can, so it's just a bit of intuition there that will hopefully help. So that's basically the idea behind this experiment here. It's only one can at a time here, just that liquid on top and the tilted angle here. So here is the actual setup here. It's running at the moment. So the heart of the system is of course the Peltier here. I've got a couple of another one here just to show you. So this is actually a couple of plastic blocks here. If I bring it up to the camera, hopefully at the right angle there, you might see the milled lines inside there. So this has got an M-shaped milled inside here, so it allows the water to go directly onto the surface of the ceramic, and that's just eliminates so much other trouble. So a typical construction like this, you have the ceramic, and then you have thermal paste, and then you have the aluminium, and then the water. So there's a whole bunch of things that can get in the way there. Not just the thermal paste, I found that even these aluminium blocks here, if they're not properly designed, they can inhibit the heat flow through there. So I thought I'd skip all of that stuff and just create direct water to ceramic here, and it works really well. They're consistent, these guys, and they're much better than, well, they're about 10% better than a really good one of these, but I've found that these are always hit and miss, so some will work and some don't. So this is a reliable and gets about 80% of the data sheet performance. So that's the heart of the system there. The Peltier itself, I've got it going through just a current controller here that I can set the current. I started off with around 2.5 amps, which is about 18 watts for the electrical energy going into the Peltier itself. And then when everything's actually cooled down, I backed it off to 1.5 amps, which is about 8 watts. In the rest of the circuit there, you've got a water pump here, which is circulating water that goes around to the top of the can. There's a tube here at the bottom that picks up the liquid and pulls it through to the other side here, and then goes through the loop there again. There's about 200 milliliters of water in there, so that also has to be cooled down as well. So when I start this experiment, everything's at ambient temperature, about 21 degrees. So that's part of the delay in the system there, will be because that needs to be cooled down as well as the liquid inside the can. On the hot side is actually, it's just a cool box here, just a cheap cool box that has about 20 litres of water that's at room temperature. So I'm not cheating there. It's not like an ice box that's got ice in it that's used the kind of coming through here to cool everything down. So it is the Peltier system that's actually creating the cold side of the circuit here. Both of the pumps are being run at about 7 volts. They're 12 volt pumps, but if I run them at 7 volts, it gets about 1 litre per minute for the actual circulation. And importantly, it keeps the heat that's in those pumps there down to about 1 watt. And that's important because you don't want to be having a really hot pump that's creating heat that the Peltier then has to get rid of again. So let me see, I've got a little checklist here to make sure I've got everything here. So the last point I think is just there's 4 sensors here on the temperature for the inlet and outlet of each side of the Peltier. So you can see there's 4 spots here for in and out for each side, and I've got that going through to a data acquisition system here that's measuring down to that thousandths of a degree that I've mentioned in previous videos, and I can use that to estimate the cooling power for the system. If I know the flow rate here, which I've measured a couple of times, I think I took about 5 measurements here to estimate the flow rate there, and then I can just multiply the maths through to figure out what's the actual cooling power that's coming out of my cold side here. So I think that's the basic system here. So the next bit will be seeing just how well it actually went. Or, well, actually, I've got a can in here at the moment. It is Sunday night at the moment, so I'm still having a few beers. You can see my red face here is because of my first beer. So I'm going to pull this out and just see. You might be able to hear the pump here is complaining there because it's got a bit of air in it, which I should really turn the pump system off when I pull it out. So I'm going to open this can up here, and I'll put in a just one of these, I guess it's meant to be for meat, but you can also use it for liquid here. So it's showing 20 degrees. Nope, it's dropping down 2 degrees. So I don't know if that will show up on the camera there, but it's running around 2 degrees there. So that's successfully cooled it down. I did remember one more thing about this setup. This container here, this is one of these insulation vacuum flask beer mugs kind of things. It's meant to be great for insulation, and it is really, really good as long as you have no moving liquid inside there. So I've done experiments with this before. They're fantastic as long as everything is very still, but when you have circulating liquid like this in there, they're actually hopeless. So I think there's some bridges between the vacuum that allows the heat to go from the hot side to the outside, or the cold side to the outside. So if I put my fingers on here, I can feel that's cold. So when I did the experiment that I'm going to show you next, that's actually going to be with bubble wrap and stuff around here as well to prevent that cold escaping out. And this just helps the cold side of the system to work more effectively because you're not counteracting that extra heat that's coming in from the environment. All right. Enough on the setup here. I will now show you the results in the next section. Okay, so how did it all work out? Well, I've got a graph here in the screen in front of me. I'll put that up on your screen in a second. And I'm just going to run through the numbers here and tell you what's going on there. So first of all, the system had 5 temperature sensors in there. There was 1 for ambient and then 4 for the in and out for the hot and cold sides of the Peltier there. For the cold side, I used the temperature difference going in and out there to estimate the cooling power. So if I zoom in here on the actual lines here, you can see a small gap there between those two. I can use that to multiply that by a factor, which I estimated from previous measurements, the flow rate of water and the heat capacity of water. Put all that together and I can come up with a factor there of 87, and then that's actually a little bit rounded down just for to account for the potential errors in the measurement system. And then I multiply that 87 by the temperature difference. So when I took this screenshot here, the temperature difference was 0.263 Kelvin, or that's 263 millikelvin. So very fine temperature measurements there. Multiply that by the factor, and I can estimate it was 22.9 watts of cooling that's going on there. So I'm using that to generate another line there in the graph. I think it's, I don't know, it's a teal color or something, but you can see the difference there. It's the one up the top here. So at the start of the test, I had everything sitting around 21 degrees at just room temperature. So this is not only the can, but the cold water loop and the hot water loop and the room temperature. Everything was all around 21 plus or minus 0.8 or something like that. Did I say 0.8, 0.2? So pretty tight temperature control there at the start of the test. And then at the 10-minute point here, I have turned the power on. I was using 2.5 amps at the start, which was drawing about 18 watts from the power supply. For that was producing a peak here of 35 watts according to the graph, but I know those sensors are a little bit slow kicking off. If I sort of draw a straight line here up to the sort of 10-minute point here, it's probably about 36 watts at the point when I turned everything on here. And that's pretty good. So 36 watts of cooling from 18 watts into the Peltier. Of course, I do have the pumps as well. That's another 2 watts there, so slightly below a COP of 2. And I could get a lot higher if I reduced the current off a bit, but I want to get things moving fairly quickly. So I think that's a nice sweet spot for this particular application. Now, what happens with the actual temperatures? So at the start of the test there, the rate of change of the liquid circuit. So this is not the can itself, but the cold side liquid, which is at 200 milliliters of liquid. That was reducing at around 2.5 degrees per minute, which I think is amazing. And then that starts to then transfer the energy to the can. So it kind of slows things down a little bit here. But in about 20 minutes, I was getting down to 5 degrees for the water circuit, and I know based on experience, I've done the test a few times, that if I then pull this can out at that point and then just mix things around a bit and put the temperature probe inside, it's about 1 degree higher than the cold side circuit there. So I would estimate that the actual core temperature inside here would be about 6 degrees when this is showing 5 degrees for that cold side liquid loop. So that's 20 minutes to get starting at 21 going down to 6. That's 15 Kelvin difference in 20 minutes. That's certainly faster than the main part of the fridge over here, and it's faster still than even the freezer compartment tests, which normally take about 45 minutes to get down to that sort of level. And I think 6 degrees it's probably just on the edge of being a drinkable beer for me. So I probably prefer 4 or 5 degrees, but I'd be happy with that if I was in a hurry. Of course, if I want to wait a bit longer, I could get that definitely down to the 3, 4, 5 degrees. What I've done here at the 31-minute point is to change the current from 2.5 amps down to 1.5 amps. That dropped the Peltier input power down to 7.5 watts. And that dropped the cooling power here down to about 11, 12 watts. You can see here that the temperature actually goes up a little bit, and that's what I mentioned in a previous video, that you can get a little bit misdirection there to think it's actually going up in temperature. But if we zoom in this here, we see it reaches a flat point here and then starts going back down again. And if we leave that for long enough, it's only 5 or 10 minutes there. If I left that for long enough, it would start to decrease in temperature down there and still get down to probably 2 or even 1 degree based on experience. So anyway, that I think was a fairly successful result there. I think they're good figures. At this point here, I pulled the can out and actually checked the temperature, and it was as expected, around that 5 or 6 degrees. And then I put a new can in here, and then it's starting to cool things down here, but I thought with that 1.5 amp setting, it's just a little bit too slow, so I bumped it back up to the 2.5 amps here, and you can see that the power here has jumped back up again, so that's starting to cool down nicely fairly quickly. You can see here that the power measurement here has gone a bit bumpy. That's probably because the activity of putting cans in and out of that system here has introduced a little bit of air into the system. piston there, so the water pump is probably not running at a nice smooth rate here. So even this estimate here probably isn't accurate anymore because of that interruption to the flow rate there. Okay, so that's it. I'll leave this particular graph here, and I'll come back with another graph showing a bit more of a longer test with more cans going in there. Okay, so I've got another graph here, which is, I won't spend too long on it. I just want to show a normal Friday night kind of pattern here, where I would take the can of beer and probably spend about half an hour for the first can. It gets it down to about 2 degrees, and a pretty chilly situation here. I wasn't too worried about the starting conditions. It wasn't a laboratory kind of test here. But yeah, that was certainly drinkable. And then the next can gets thrown in straight into the system, and then I leave it for about 45 minutes, which is, I don't want to be drinking beer too quickly here. So after that 45 minutes, it was hitting 0 degrees for the water loop, so it's getting close to freezing. I don't want to put antifreeze and stuff into the water loop, so I will back that off there. For the next one, I dropped the input down to about, I think, 15 watts for the whole system, including the water pumps as well. And that nicely brought that down to about 2 degrees after the end of the 45 minutes. And then I just kept doing that with loop after loop. I think the last one there, I took a bit longer to have the can of beer. But yeah, it shows that this kind of system here is working as a regular way to cool cans of beer down from room temperature without any problem. And it's running on about 15 watts there. So I think pretty cool. All right, I'll leave it there and then go to the final thoughts and some ideas about how I could improve the system. So first of all, I want to focus on the amount of energy that I was using, or the power that I was using. Is about, I think, 20 watts to start off with, and back down to about 10 watts in the lower power setting there. Some people might think that's still a lot of energy relative to a normal fridge. So this particular fridge here runs, I measured it over a 24-hour period. It was 43 watts, which is, kind of crazy. They do a fantastic job with a very, very small amount of energy or power. And considering all the things it's doing, it's lots of stuff in there that's been kept cold, and ice compartments and freezer boxes and stuff like that. It's amazing what it does. But it's still actually quite competitive. The numbers do run fairly similar between my system and just a normal fridge. The thing is, you can't get around the basic physics here. As I mentioned before, you'll need about 20 to 30 kilojoules of energy to cool this down 15 to 20 degrees, just based on the pure thermal mass of this as well. And with a fridge, if you're going to be opening freezer drawers or doors and stuff like that, every time you do that, you probably leak around 2 or 3 kilojoules of energy just from that particular action. You're going to have to do it twice. If I'm going to put this into the freezer compartment here, that's could be 5 kilojoules of energy that I'm losing there. And on top of that, fridges only have a COP of about 1. Now, I know a lot of people are going to argue about this. They say, oh, no, compressors are 3 or 4, my air conditioner up here, they're 3 or 4 COP. This is totally untrue. The reality is that compressor-based systems are wildly all over the place for the COP, depending on the conditions. The problem is that we can't actually measure it. It's really, really difficult to measure the amount of heat coming out of an air conditioner or the amount of cooling that you're actually getting in a fridge. So everyone just goes off this industry figures of about 3 or 4, and they just leave it there. But the reality is a fridge is actually driving against a massive DT. It's about 70 Kelvin when you take into account the temperature on the hot side, which is probably around 45 degrees, and the cold side, which needs to be about, I don't know, minus 25 in order to get the heat or the cooling to transfer into the freezer compartment. So it's not the room temperature minus the minus 18 degrees in here. You have to look at the temperature difference of the actual compressor cycle itself, which is much, much larger. And at that point, you just cannot fight the physics. You are not going to get a COP of 3 or 4 there. It's just, even in the perfect Carnot system, it's about 3.5, and a normal compressor will get 50 to 60% of that. So you're looking at a COP of about 2. But on top of that, fridges are designed horribly. They actually use the outside skin of the fridge to get rid of the heat. So you've got like a box within a box where you're putting your heat on the outside of the box. So of course you're going to get a lot of leakage between the outside skin and the inside compartments there. It's done for form factor. It looks really nice, but it's not a very smart way to get rid of the heat. You're better off maybe having a compartment on top of the fridge that rejects the heat, so it's well away from any of the cold compartments in there. So at the end of the day, when you add all that up together, you get about a COP of 1, which means that my system is actually doing better than that putting a can of beer into the freezer compartment to chill it down in 45 minutes. So my system is faster and it actually uses less electricity than a normal fridge would do. So with that point of view, I think the system itself is pretty good. Of course, it involves its water and stuff, and I do have that dirty big tank of or the esky with the 20 litres of water in there, so I want to think about how to improve that. I could probably get away with maybe 5 litres, I don't know, as long as I can get rid of that heat to the environment somehow. I don't want to introduce fans to this system. I'd like to just keep it to that 2 aquarium pumps there, but there should be a way to maybe circulate the water through some black painted pipes or something like that that'll allow me to get rid of some of that heat into the environment. It's not that much heat, it's probably only 40 watts or something in total, so it should be possible to do that there. What about the Peltier side? So what could I do there? Maybe I could put some Peltiers in parallel, which is not too difficult to do, or I could stack the Peltiers. It turns out plus minus points on both sides. So the parallel condition here with 2 Peltiers pumping together, you'll get some really fantastic cooling there, because you could probably easily get 70 watts of cooling, and 5 degrees per minute kind of stuff is possible. But once the temperature starts going down, you get that 15-20 degrees below ambient, this kind of system starts to fail, because you get each one of these is going to be leaking energy back through the Peltier there. So it's about 1 watt per Kelvin, or 1 watt per degree. So at 20 degrees difference from the hot side to the cold side, you'll be leaking 20 watts back through here. So you've got 2 of these, you're going to have 40 watts of leakage through here. So that's a bit of overhead there that you don't really need for just maintaining a can of beer at, say, 3 degrees. What about the parallel one? Well, that actually surprisingly can work more efficient. If you go through the modeling and the numbers, it's possible to get, did I say parallel? Not stacked version anyway. And the benefit of this is that you're actually doubling up on that thermal resistance here. So you end up with 2 Kelvin per watt for the resistance. So you're only leaking 10 watts through this system here at a temperature difference of 10 degrees. I think, though, for me, I would stick with just the simple 1 Peltier solution, and I'd probably push it a little bit harder and then cool it down to, say, 2 or 3 degrees, and then turn everything off. Turn the Peltier off, turn the pumps off, and it should actually hold the temperature fairly well, so maybe 5 or 10 minutes. When the temperature goes up to maybe 5 degrees, turn the system back on again, and then do that kind of cycling. I suspect that's going to be a more efficient solution than trying to mess around with parallel or series Peltiers there. Okay, so that's it. I've probably waffled on for too long here. I hope you've enjoyed it. If you have any questions or comments, you can hit me up down below in the YouTube comment section, or email me. Again, I'll throw up that email at the back end of the video. Hope you've enjoyed it, and yeah, we'll be back again with more in the near future. Catch you later.